Question number 2 gives us a small body of water with a circuit in it, and it gives us an initial temperature of that water, and it asks us what the temperature of the water will be after 1 hour if this circuit is running and that resistor is giving off heat into the water. So we know we've got 10 kilograms of water, and so it's going to be a little bit of a combination of thermodynamics and electrical engineering here to find our answer. And this is actually very similar to a problem that I was asked during my technical interviews last year. So definitely know how to do this one. It is a good one to know, and it's not too difficult once you understand the key concepts. So starting off with our kind of 2 equations that we're going to be using here, we've got our specific heat capacity equation, where we have Q as our heat in joules is equal to M, which is the mass of whatever we're working with, times C, which is the specific heat capacity of whatever we're working with, times the change in temperature. And then we've got P equals IV, which is just our power equation from electrical engineering, which says power is equal to our current times our voltage. So if we think about how we're going to relate these 2 equations, Q here is in joules, and power is watts, which is equal to joules per second. And so we've got joules and joules per second, and our equation tells us the time frame is 1 hour, which is just 3,600 seconds. And so if we can find the power going through the resistor, then we can just multiply that power by the 3,600 seconds in order to get the joules. And then we can plug that into our specific heat capacity equation and solve for our delta T. To start, we know that P equals IV, but in this equation, we're only given V and R, we're not given I. So we could go and use our Ohm's law, V equals IR, and solve for our I. Or what we could do is just to plug that directly into our power equation, because we know that I is equal to V over R. And so we can say that P is equal to V squared over R. With that knowledge, we know that P is equal to our V squared, which in this case is 10 volts squared, over R, which is 5 ohms. And we get that our power is equal to 20 watts. Now we just need to relate this power to our Q, or our heat added. And so as I mentioned before, watts is just equal to joules per second. So our 20 watts is equal to 20 joules per second. And our Q, our heat added, is in units of joules. And so in order to get that watts into our joules, we're just going to have to multiply by the number of seconds. And so to do so, we can say that our Q is equal to 20 joules per second times 3,600 seconds, because that's how many seconds is in an hour. And that leaves us with 72,000 joules. Next, let's plug this number into our specific heat capacity equation. And so we've got Q equals MC delta T. And so plugging some numbers in, we've got 72,000 joules is equal to our M, which is our mass, and we're given that that's 10 kilograms of water. Our C is our specific heat capacity of water, and that is something that would probably be good to know. It's 4.186 joules per gram times degrees Celsius. And then we've got our delta T, which we can say is T final minus T initial. And we know that our T initial is 20 degrees Celsius, so we can just plug that directly in. And so now we're left with one equation and one unknown, and we can solve for our final temperature. One important thing to note in this equation is that we've got 2 separate units of mass here. We've got our kilograms for our mass of the water, and then we've got grams in our unit of our specific heat capacity. And so let's convert that specific heat capacity into kilograms so that everything is consistent and we're not going to have any problems with our units. So we've got the 72,000 joules equal to 10 kilograms times 4,186 joules per kilogram degrees Celsius times our change in temperature, which is TF minus TI. And the reason it went from 4.186 to 4,186 when we were going from grams to kilograms is because that unit of mass is on the denominator. If we do out the math, we'll find that our units cancel nicely and we're left with T final minus that 20 degrees Celsius is equal to 1.72 degrees Celsius. And so that leaves us with T final is equal to 21.72 degrees Celsius. And so that's how you do this problem. Hope that helped.